In this section, we'll take a look at the protocol-independent routing concepts objective of the JNCIS service provider exam. We'll examine static routes, routing instances, and load balancing. For more detailed coverage of this objective and more, please check out the JUNOS Intermediate Routing course.
In this section, we're going to examine some of the various different ways that you can statically configure routing on a Juniper device. And I've drawn up some example configuration here on the left-hand side of the board. All of this statically configured routing appears under the routing options stanza of Juniper configuration. And the first type of statically configured routing that we're going to examine is static routing itself. So that's this chunk of configuration here. And with static routing, as the name suggests, we're statically specifying routes and where we want to send traffic that's encompassed by those routes to. And we do this by configuring a route that encompasses the destination IP addresses that we're going to be sending traffic to, and a next hop. And that's the forwarding next hop, where we're sending traffic that appears in this route to. And we can configure multiple next hops and associate them with routes. And by default, when we associate multiple next hops with a route, depending on some other configuration, we're probably going to load balance traffic across those next hop destinations. If you were configuring multiple next hops, in the configuration here, what you would see is you'd have the route specified, then you'd have next hop, and instead of having one next hop listed here, you would have square brackets. Contained within that square brackets, you'd have a list of the next hops that you're routing to. So this is all well and good if you want to send traffic to all of those next hops. But maybe you want to have one of these next hops to be only used in cases of failure. So you're configuring multiple next hops for resiliency. If you're doing this, if you're configuring multiple next hops for resiliency, instead you want to use this qualified next hop syntax. And in the example configured here, we've got the main primary next hop configured with the next hop syntax, and we've got a qualified next hop configured using the qualified next hop syntax. And using qualified next hop, what this allows us to do is to change the metric and or preference of that next hop. And so that means that we can tell the router which next hop we want to use under normal conditions. In this example here, we've configured the qualified next hop to have a preference of 6. And if you remember back, the default preference of static routes is 5, and we're preferring lower preference over higher preference. So in this case, under normal operation, we're going to be using the next hop 10.1.1.1. In cases of failure, where this next hop is unavailable, we then start to use the qualified next hop that we've specified of 10.1.2.1, because we've specified a preference of 6, which is greater than the default preference of the static route. If we wanted to alter the defaults of all static routes from that, say, preference of 5 to another value, another preference value, another metric value, we can do that. And we would do that under the static and then defaults stanza within the configuration hierarchy. And you could also do things like associate all of your static routes with a BGP community to be used later when you're redistributing those routes into BGP. So that's static routes covered. Now let's move on to aggregate routes, which is this part of the configuration syntax that we've illustrated on the board. And aggregate routes are used for address summarization. So you're doing this for routing simplicity, and you're doing it to save resourcing within the control plane of your network. So if you have multiple networks existing on your router, and you want to, instead of advertising multiple routes that describe those networks out to the rest of the network, you want to advertise one covering route that summarizes all of those routes, you do this with the aggregate root syntax. And the configuration is very similar to that of static roots. So we're specifying the root and we're specifying the network. The key thing to note here is that this root does not appear in the routing table until there is one or more contributing roots. So that's one or more roots that are more specific than it, that are appearing within its definition. So in this case, if we had 10.0.1.0/24, that appears within 10.0.0.0/22. So it's a contributing root. So this root then appears in the routing table. And aggregate roots are used for this address summarization and for control plane advertisement upstream. They're not used for actual forwarding traffic once that traffic arrives on the router. They can attract traffic to that router, but they're not used for forwarding traffic onwards from that router. And when traffic arrives on the router with a destination IP address that's described by an aggregate root, but is not matched by a specific route, then by default, the router is going to send ICMP destination network unreachable messages back to the source IP of that packet. If you don't want to be sending ICMP messages back to packets that are described by aggregate routes that aren't matching specific routes, then you use the discard flag. And what this means is that traffic is then silently discarded rather than sending ICMP unreachable messages back. So that's aggregate routes described. Finally, let's now move on to generate routes. And generate routes behave in much the same way as aggregate routes, in that they're only going to appear in the routing table if there are contributing routes that are contained within the route that you've defined. In this case, we've defined a default route. So any route in the INET0 routing table is effectively going to be a contributing route for this generate route, and it's going to appear in the routing table. You can filter what routes are allowed to be contributing routes. And if you were to do that, you use this policy syntax. So for example here, if we only wanted routes to contribute to this default route that are contained within, say, 192.168.1.0/24, you would make this policy statement here only match on this network. Then only this network can act as a contributing route for the generate route. So any other routes in the routing table are not going to cause this route to be generated. The application of a filtering policy is also applicable to aggregate routes. So now we come to the main difference between generate routes and aggregate routes. So if traffic is sent to a device with an aggregate route, we've already mentioned if there are no more specific routes, we're going to be sending ICMP unreachable messages, or we're going to be silently discarding the traffic. The difference with a generate route is that the generate route takes a forwarding next hop from the primary contributing route. So when traffic arrives that's described by this generating route, you're going to forward traffic as if that traffic was identified by the route that is contributing to its generation. And you will typically use generating routes for a route of last resort, so an emergency route to get traffic off your device in cases of network failure. Or you could also be using it to generate locally a default route that you're then going to be onward announcing to, say, a customer that's connected to this routing device. And this is a quick overview of the static configuration for routing that you can apply to a Juniper device. In this section, we're going to take a look at routing instances. So on every Juniper router, you have a master routing instance. And within that master routing instance, you have multiple routing tables. And these routing tables perform different functions across different address families. You have the INET routing tables that are providing functionality for IPv4 address families, and you have the INET.6 routing tables for IPv6. The .0 routing tables are the main routing tables where you do the bulk of your IPv4, IPv6 packet forwarding. INET.2 is a routing table sometimes used for RPF checks for multicast traffic. So that's RPF checks against multicast sources when you don't want to be performing those RPF checks using your main INET.0 routing table. The INET.3 routing table is used for taking IP traffic and pushing that IP traffic into LSPs, and for that traffic to then be MPLS label switched further downstream in the network. And it does this by being populated by the IP endpoints of the LSPs that you have established in your network. And we'll examine INET.3 in a lot more detail in subsequent videos. So you have these routing tables associated with your master routing instance on your Juniper routers. And if you configure additional routing instances, then you also have copies of all of these routing tables associated with those routing instances that you create. So for example, say you have routing instance RI-A, you create that routing instance. Now within that routing instance RI-A, you have the routing table RI-A.inet.0, RI-A.inet.2, and so on for all of the other routing tables. So this is what happens with routing tables when you create new routing instances. Why do we want to create new routing instances on a Juniper router? What we're doing is we're logically segmenting a router into separate logical tables, and we can use those different logical tables for different purposes. So some of these reasons would be, say we are a service provider and we have multiple customers and we want to provide routing to those customers, but we want to keep those customers separate from each other. And we can use routing instances to do that. We could also have different services. We want to route traffic for those services across different interfaces and different routes in our network. Again, we can use routing instances for that. There are many different reasons to use routing instances, and we'll explore some of them in more detail in subsequent videos. So that's why we might want to use routing instances. How do we configure routing instances? Well, there are three main things we need to do when we're configuring routing instances. We need to associate them with logical interfaces. So these are going to be the interfaces where we send traffic into a routing instance and receive traffic coming out of a routing instance. We also need to configure routing in a routing instance. So we need to know the destination networks to which we're going to send traffic across those interfaces that we've associated with that routing instance. And you configure routing within a routing instance much like you would configure routing outside of a routing instance, just standard on a Juniper device. And finally, we need to configure the type of the routing instance. And the type of the routing instance is tightly linked with the reason why we're deploying those routing instances in the first place. If we're just creating logically separated routing tables, then we would use a virtual router type. If this was a MPLS VPN environment and we have different routing instances for different customers, we'd use a VRF type. There are lots of different variants we could use if we had layer 2 VPNs configured in a service provider environment. And depending on the layer 2 VPN type, we would configure a different routing instance type. on our deployed devices. Sometimes there comes a time where you need to interconnect different routing instances. You need to be able to send traffic from one routing instance into another routing instance. And there are many different ways that you can do this. The first interconnection option we can have is that we can have a physical loop. So this is a piece of copper or fiber on your Juniper device interconnecting with one physical interface that's associated with one of the routing instances, and it's looping to another physical interface that's associated with the other routing instance. And then, as you would an interface facing a neighboring device, you would run routing protocols over this physical loop. You could have static routes, you could be running BGP sessions, OSPF sessions, etc. And this is a fine way of doing the interconnection. However, obviously you are burning revenue-facing ports here. So if you want to maximize the number of ports that you can use for revenue-generating services or interconnections to other routers, then perhaps this isn't the best option for you. So another option is to use a logical tunnel. So again, we're doing exactly the same thing. We're interconnecting the two routing instances via a specified interface. It's just in this case, we're using a logical tunnel. So this is a logical construct that exists only within the router. And we interconnect those routing instances using this logical interface. Another option is that we can leak routes between these two different routing instances. And there are a number of different ways that you could do this. The first is that you could use an instance import policy. So in this example here, you would configure an instance import policy within routing instance RIB, and you would tell it to import some or all of the routes from routing instance RIA. And that way, those routes will then facilitate intercommunication between those two routing instances. And the final option, perhaps the most complicated option, is to use RIB groups. And RIB groups are this arrow at the very top of this diagram here. And I'll attempt to explain how RIB groups operate in the final part of this video. So on any given router, you have lots of different sources of routes. They could be routes that are associated with interfaces. They could be static routes that you've configured. They could be routes learnt from dynamic routing protocols. And you have all of these sources of routes that are populating routing tables within a router. By default, with no extra configuration, no routing instances configured, these sources of routing protocols are populating these kind of tables here. If they're IPv4 routing protocols, they're populating the inet.0 routing table. But maybe we want these routes to populate more than one routing instance. And we can do that by using RIB groups. So what we do is we configure a RIB group and we associate it with the source of the routes that we want to send to multiple routing instances. So say, for example, here, we want to send the route that we have associated with interfaces on a Juniper device to multiple routing instances. So we associate interface routes via a RIB group. And then we configure this RIB group to have an import RIB of the tables that we want to send those routes to. So this is the configuration I have illustrated down here. So we define the RIB group, we give it a name, and we specify the import RIB. In this case, I've listed ri-a.inet.0, ri-b.inet.0. So the IPv4 routing tables in these two routing instances. And with this RIB group associated with interface routes, what this means is that all of those interface routes are then imported into these two routing instances. So we have the interface routes present in both of these routing tables. And because those routes are in both routing tables, we can then facilitate routing between them. And rib groups are incredibly flexible. If you wanted to have more than 2 routing instances taking those routes from interfaces, you could absolutely do that. If you wanted to have static routes and OSPF routes and BGP routes propagated into those separate routing instances, you can absolutely do that. All you need to do is associate that rib group with that source of routing information. And one final thing to note with rib groups, we won't dwell on it too much here, is that what we've talked about here is the import rib part of the rib groups, which is controlling the flow from the routing protocol, from the root source into the rib group, into the ribs. The export rib is controlling routing flow in the opposite direction. So that's going from the ribs via the rib group to the routing protocols. And it's not covered in this set of videos here. It's not tested on the JNCIS service provider exam, but this would be used in a multicast environment that we mentioned earlier when we were using inet.2. And you'd be telling multicast protocols which rib to use for its RPF checks. This is a quick overview of routing instances on Juniper devices. In this section, we're going to take a look at load balancing on Juniper devices. So in a typical network deployment, it's highly likely that you're going to encounter scenarios where you have multiple paths that have the same cost, have the same IGP metric that occur between 2 router pairs. And in an ideal world, you're likely going to want to send traffic over all of those links that have the same cost between 2 routers. On Juniper devices, by default, you're only going to be picking one of these links to send traffic over. This is a suboptimal situation. It can mean that you're lacking ways to increase capacity between 2 devices. So let's walk through how Juniper devices operate by default and how we can fine-tune that behavior so we can spread traffic over multiple equal cost paths between 2 routers. And so to illustrate this, I've drawn up a very, very simple topology that has multiple equal cost paths between 2 routers. This is what we have here on the uppermost part of the right-hand side of the board. We have a sending device, and he's sending traffic to this destination network of 192.168.1.0/24. And this traffic is passing over 2 routers, and these 2 routers are interconnected via 2 physical interfaces. So by default, what's going to happen when traffic from this host reaches this first router that has the 2 parallel links to another router? So if we examine what's going on in the routing table, in the routing information base of this router here, I've drawn a summarized version of what you're likely to see on the board here. So we have our destination network, and this is associated with the 2 next hops that have equal costs that relate to the 2 physical interfaces. So we've got one going via Gigi 000 and one going via Gigi 001. And in the routing information base, one of these next hops is going to have an arrow next to it. In Juniper CLI terminology, this arrow means that this next hop has been selected as active. And it's going to do this in a randomized fashion. So one of these next hops is going to be chosen at random to be programmed to be forwarded. So what the router now does is it takes this routing table and it converts it into the forwarding table, into the forwarding information base, for it to be programmed into the packet forwarding engines of the line cards of that router. This is what I've illustrated here on the board. So in the routing engine, the rib is converted into the fib, and that fib, that forwarding information base, that forwarding table, is then programmed into the PFEs, the packet forwarding engines, of the line cards, the data plane of the routers and switches, etc. And so what we're going from is we're going from this style formatting in the rib to this style formatting in the fib. And you can see here we've only programmed one of our two next hops into the fib. So we've got our destination network, its next hop, we're programming a unicast, a ucast next hop, and we've got the associated interface. So by default, what we're doing here is traffic from this host is arriving at this router, and we're sending all of the traffic to this destination network across this upper interface, this GigE 000. GigE 001 is being completely unused. And so obviously this situation is undesirable in most cases, certainly. There are some cases where you don't want to enforce load balancing, but for the majority of cases you do. Generally what we want to be doing is we want to be using per flow load balancing. And per flow load balancing is the only real load balancing that's supported on modern Juniper devices today. And what we're going to do is we're going to use some characteristics of the IP packets that are arriving on this router. And using those characteristics, we're going to determine what packets belong to a given flow. So, for example, this could be things like source and destination IP address, source and destination layer 4 port, and layer 4 protocol. So say if this was a TCP session running from this host to a host on this destination network, we'd use the source and destination IP address, source and destination port, and the fact that it's TCP to identify that all of these packets belong to a common flow. And then what we're now doing on this router here is that we're going to be hashing on a per flow basis. So this means that this flow and all packets belonging to it are going to be hashed onto this top interface, and packets for a different flow are going to be hashed onto the bottom interface. So how do we turn on per flow load balancing on Juniper devices? Well, let's go back and take a look at this flow where we take routes that are programmed in the rib to routes programmed in the fib. There's actually a policy control point in the routing engine between the rib and the fib, and we can apply policy statements via export point between the rib and the fib, much like you would apply a policy statement with standard routing protocols. And you can perform similar actions to policy statements that are applied to routing protocols. You can be filtering routes, for example. You could be modifying the criteria of those routes. And this is exactly what we want to do here. We want to modify the criteria of some of these routes. In this case, we're using a then action of load balance per packet. And you may think, well, we've just talked about per packet versus per flow, and you said Juniper only do per flow load balancing. So why are we using a per packet action at this control point? Well, this just dates back to the legacy design of the Juniper CLI, when per packet was an option. So just remember that Juniper routers only ever do per flow load balancing. It's just that when you're turning it on, you need to use the per packet flag in the policy statement when you're configuring that Juniper router. So say now that we have applied a policy statement at this export control point, and we're taking this rib entry, this route, and we're converting it into a fib entry. And the fib entry that we create from this with per flow load balancing enabled looks a little bit like this down here. Again, I've kind of summarized this. It will look slightly different on an actual router, but there's enough information here for you to understand what's going on. So what we're now doing is that we're inserting an intermediary data structure between the route, the destination network, and the next hops that we're binding it to. And this is a unicast list, a ulist data structure. And this unicast list data structure consists of all the next hops that we're binding to our destination network. And you can see here we've got two unicast next hops bound to our destination network, which constitutes the two physical links that we have interconnecting these two routers. And this means that we're then going to hash across these two next hops, meaning that we're hashing on a per flow basis across these two links when we're sending traffic from this router to this destination network. And this is a quick overview of load balancing on Juniper devices.